Now let's look at lithography. Lithography uses scanning power microscope. The first one is the atom and the particle manipulation by the HTM or AFM. So here's the idea for this process. So for example, you have this atom here. You have this atom is here. So you approach the tip to this atom, and then you apply some electrical field. There is the force. There will be the electrostatic force, and there will also be the van der Waals force. Then you move the tip along the surface. This way you can put the atom wherever you want. So the field cannot be very high. If the field is too high, then the atom will be picked to the tip. Then this is not good. So we need to keep the atom dragged along the surface rather than going to the tip. So the field cannot be very high. So obviously this is the ultimate resolution for the lithography. What do you get? You get single atom resolution. You can move the atom by atom, so you get a single atom resolution. So this is the first example. In this case, we have 48 iron atoms. 48 iron atoms arranged on the copper 111 plane. This is the cobalt atom on the copper 111 plane. This is carbon monoxide molecule arranged on the platinum. This one is the iron and copper. It's also iron copper. This is the Chinese word. It's also Japanese word for the atom. So we can do similar process. In this case, so we have this carbon nanotube. So we can use the AFM probe to move around to modify the carbon nanotube. You can, for example, in this case, you can put the carbon nanotube below the gold. There's the source drain and there's the gate. This way you can make some devices. But in reality, this process will not be, it's only for research, no commercial value, because this is very hard to work with. So this is the first idea, AFM manipulation and the atom and the nanoparticles. So now let's look at second example. That is the AFM oxidation of the silicon or metals. So in this case, so you have the probe, you apply a voltage. This is the anode, this is the cathode. So this process is also called anodization. It's oxidation is also called anodization because the substrate here is put in the anode. This anode. So here we apply a voltage, and when we do the experiment in the environment, not in the vacuum, there is always humidity. So when the humidity is higher than about 20% humidity, there will be water. Water will be condensed. That means this is the electrochemical process. So then it will be a electrochemical process. So we have the water, we have liquid, we have ice, we have liquid. This is an electrochemical process. So how to prepare the sample? In this case, for the case of silicon, so we prepare the sample such that the surface will be terminated by the hydrogen. So how to make the surface hydrogen? So one way to do this one, to do it, so you have the silicon surface here. So normally the silicon surface, if you do the clean well, it will be terminated by the hydroxyl group. But if you put this one in a hydrofluoric acid, so in the silicon, usually there is a native oxide. You have the native oxide. So this is the native oxide. So when you put in the HF solution, it will remove the native oxide. It will activate the native oxide. At the same time, the surface will be terminated by hydrogen. So when it's terminated by hydrogen, it becomes hydrophobic. So you can see this. You take the wafer away. So you take the wafer out. It become the water will fall off. It become hydrophobic. In this process, we apply a voltage. This voltage here will pull away. We will apply the voltage and pass the current, so the hydrogen will be pulled away. And when the hydrogen is pulled away, you expose the bare silicon. The bare silicon will be oxidized in the environment, so you form a layer of oxide. But before that, this hydrogen here is like a protection or passivation layer. But when this is gone, no longer the surface no longer passivated, no longer protected, so it will be oxidized. So how thick oxide you can grow? How thick the oxide you can grow? You cannot grow very thick because once you have this oxide layer here, it will become insulating. It become insulating. But for this process, we need to pass electrical current. We need to have electron flow from the tip onto the constant electron flow from the tip onto the substrate to dissolve the hydrogen. So we need a current. But once you have the oxide, this is insulating. This will stop the current. But that means the process is self-limiting. After a certain thickness of oxide, like 1 nanometer, you can no longer do this because the surface become insulating. But there's one way to make the surface hydrogen. But I talked to another a professor who worked on this process. So he said a better way to prepare the surface with hydrogen is to bombard the silicon with the hydrogen ion. So when you bombard silicon with hydrogen ion, you can also get the surface hydrogen. So obviously, this process depends on the voltage. Higher voltage, faster and wider lines. The scan speed slides from the no scan to 10 micrometer per second. So we have faster scan, you get smaller lines. Humidity. So normally we need humidity higher than 20% so that we can have the water condensation here. But in this case, for this example here, it's only 14%. So 14% may also work, but lower than that, it will be harder and harder to work. But this 14%, you get 22 nanometer lines. This one is 61% humidity here. You get 200. You get this one maybe 80 nanometer lines. This one is 25 nanometer dot. But this process is not very efficient. So here is the example. So you pass the current, you pass electron go from here to the substrate to dissolve to the hydrogen. So this is the yield. This is the desorption yield. The unit is number of atoms per electron. So you can see it's 10 to minus 6. That means so we need about 1 million electron. We need 1 million electron in order to dissolve one hydrogen atom. So it's not efficient. You need this 1 million electrons, pass 1 million electrons from the tip to the sample in order to dissolve one hydrogen atom. So here's the example of the desorption. So this part here you have the hydrogen atom. This letter here, this M letter here, there is no hydrogen. The hydrogen from this place is dissolved by this process. So as we said, the process is self-limiting. You can have only about 1 nanometer, because once you have this 1 nanometer silicon oxide, it becomes insulating. Then you can no longer pass current, so it will be stopped. So how can we do the pattern transfer using just 1 nanometer thick of oxide? This can be done by the QH etching, wet etching. So we know that the QH etching of the silicon is isotropic, and it has the selectivity about 1000. But this one, you get this high selectivity at room temperature, 20 degrees. So we do the QH etching at room temperature, you get this selectivity. We'll do at higher temperature, like 70 degrees, then the selectivity will be about 200 to 1. So if we do lower temperature, you get this high selectivity. So with 1 nanometer thickness of the oxide, you can go to about 1 micrometer. In this case, it's 690 nanometer. So this will work only with the 110 wafer. Because for the 110 wafer, you have this 111 plane perpendicular to the wafer. So the side wall, this is the 111 plane, this is the 110. So this one, is 90 degree. So here's the same idea. You have this. The 111 plane will not be etched. So the etch will only along this 110 direction, but no lateral etching, because the lateral is the 111 plane. So this for the 100 wafer. So we have the so this for the 110 wafer. We have this 100 wafer. If we start with the 100 wafer, what will happen? So you have the mask. You oxide the mask here, oxide the mask here, oxide the mask here. But what will happen if we start with the 100 wafer? Then the pattern will be something like this. it will be a V-shaped, because this is the 111 plane. So the 111 plane is not perpendicular to the 100 wafer. Now let's look at another example of the lithography using HPM. This is the dip pen nanolithography. As the name indicates, this dip pen nanolithography. So we use the AFM probe as the pen. Then we dip it into the ink, dip the pen into the ink. The ink can be like DNA or other biomolecules like protein, antibody, antigen. So this way, we can transfer the ink from the pen to the substrate. Then we can make the ultra high density gene tips with the DNA on the substrate. Very high density gene chip. This one is developed by the professor Chad Merkin from the Northwestern University in the US. This university is very close to the city of Chicago. So he started a company called Nano Ink. This Nano Ink the company here developed the dip pen lithography. So effectively, it is a kind of AFM. It is similar to the AFM, but you transfer the liquid from the AFM tip to the substrate. This one resembles macro content printing, as we learned in the previous lecture. Macro content printing. The difference is that for the macro content printing, we copy the pattern from the mold onto the substrate. So we transfer the biomolecules and other chemicals from the mold into the substrate. We copy the pattern. But this one, this pen lithography, so we created the pattern. We created the pattern pixel by pixel. But because we created the pattern pixel by pixel, it is very slow. It is very slow. But this one we copy the pattern very fast. This one we create the pattern very slow. Here's the idea. So first we dip the pen, we dip the tip into the ink. We have the ink. There will be lots of ink. Then the ink molecule, when you bring the tip to the near the sample surface, there will be water meniscus. When you have the humidity, you form a water bridge. Then the ink molecule will be transferred from the tip onto the substrate. You move the tip around. This way, you transfer the material. You can have the pattern on the substrate. This is the idea of the dip pen nanolithography. So what can be the ink material? So when we talk about macro content printing, we say that for the ink, we need to form something very stable. For instance, to water, or maybe solvent like IPA, isopropyl or water, they will not be the ink, because when they come to the wafer surface, they will be vaporized very fast. So to have stable ink, again, we need self-sampled monolayer. For the case of gold, if the substrate here is gold, and this one is gold, the water will be the self-sampled monolayer. As we see from the macro content printing, so the ink should be something like this. So when we have this cell group, cell group, it will form self-assembled monolayer onto the gold surface. This one is very good for research. You can do a lot of biological studies, and people buy this tool to do the experiment, and they publish many very good papers. But this is obviously not good for the production because of the low yield and not easy to control. So here are the examples of the dip pen nanolithography. The first one is the NU. NU is NU means Northwestern University. In this case, we have 15 nanometer line width, a very high resolution. The molecule here is this one, a 16 mercaptol hexadecanoic acid. So one end you have this cell group. You can see here. You need this one to bond onto the gold substrate. The other end you have this acid group, COH. But this one is the alkane cell. This alkane cell pattern onto the gold, also onto the gold. But this molecule here is different from this molecule here. You can see you can do very good alignment between the two patterns. On the right side is the Richard famous historic speech written in the dip pen nanolithography. I'm sure you remember what is written here. the famous sentence is that there is plenty of rooms at the bottom. There is plenty of rooms at the bottom. So this one is considered as the starting point of the nanotechnology. So at the moment, this company here is still survive. It's not a very big company. They do not, because it's only researched by the equipment, but they still survive to have this kind of equipment for the deep pen lithography. So here you have this MHA. So this is MHA acid. So you can do further. You can do more than that. So here you have the MHA coated onto the gold surface. Then you can passivate. So look at the area here is passivated. And then you can do the protein binding, binding absorption. So here you have this acid group. You have this acid group. But this acid group will absorb the protein, like IgG and lysozyme. Absorb. Then you can bind to anti-IgG binding. This way you can do some biosensor biodetection. Here is the ultra high density of the DNA array. There's DNA array by the deep pen lithography. This one is the protein. A different color is because different protein or different DNA they are tagged with the different fluorescent dye molecule. This dye molecule. Here is the you can also make the virus. So I visited this professor's group maybe 5 years ago. In the lab, in his lab, he had a very, very big lab. He put all kind of this kind of drawings, this kind of patterns on the wall to show the deep pen nanolithography. For example, you can make Einstein's face using deep pen lithography. Then he puts it on the wall to show the lab. Here is another example. This is called nanoscale dispensing. You drill a hole onto the tip. Then you transfer some liquid onto the substrate. In this case, it's called a glycerol. This molecule here, glycerol. Why we choose this molecule? This one is a liquid. It is a liquid, but it is very viscous, very thick, sticky liquid, with very high boiling temperature. So it is not volatile. So it can stay on the surface for a longer time. So we know that this material can be used for the car, for the antifreeze, or the coolant or antifreeze. Because if you add this material into the coolant will not be boiled. It will, the water. If you add this material into water, the boiling temperature will be very high. So how to make this pen? Well, this pen is made by focused ion beam milling. You do the focused ion beam milling. You can mill the hole through it. You get this pen. This is another example of the deep pen nanolithography. In this case, the same China American group, the same group from Northwestern University, they patented a tumor marker. They patented the tumor marker. So you patent some antibody or antigen, then you can catch the tumor marker from the solution. So tumor marker is found in the blood and other body fluid or the tissues. A high level of the tumor marker means you have the cancer. That means by the detection of the tumor marker, by this array, you can do the early detection and diagnosis of the cancer. Another application for this kind of study is to use the tumor marker to assess the cancer's response to the treatment and to check for the recurrence. So the main limit for the deep pen lithography is the low yield. It's very slow. If you have only one pen, it's very slow. To solve this problem, the same group, the China American group, they make 55,000 pens. You make a 2D array of the pens. The material here is I remember it is the PDMS, soft PDMS. Is this PDMS or it may be SO8? PDMS or SO8. So you can use a deep pen. You can have 55 of the pens. Then you can make the pattern and make 55,000 identical patterns at the same time. This way you can have higher throughput. But still, you have to make all the patterns at the same time, because each pen, they are not individually controlled. That means all the 55 copies, they have to be the same pattern. You cannot control each pen individually. This is the limit. So now we will continue with other types of the lithography using scanning prober microscope. Now we look at indentation, scratching, and thermomechanical patterning. So this is a very simple idea. You do the nano indentation. You just push. You apply a high force. This is the 15 micronewton, 20 micronewton, 25 micronewton. You push. You make some hole patches on the substrate. This one, you do the dip pen. The shape of the tape is triangular shape. You get this triangular shape of the patent into the diamond-like carbon film. So we can also do the scratch. We can also do the scratching process. So in this case, we will have the tape, we drag along the surface, we apply some force. We can get this is like the polymer, so we can have a 1.5 nanometer deep scratch into the polymer. We can also scratch into the silicon. We can also scratch into the silicon. But then the material, the tape has to be very hard. The tape material is the diamond. If you know the diamond can scratch into the silicon. But this one is a demonstration that it will work, but obviously there is the limit. The main limit is the tape wear. If you do a lot of this process, the tape will be worn out. It also found the debris. This is another problem. But this is easy and cheap way to do some very simple nano-lithography if you do not have access to the clean room. So we can do something similar on a self-assembled monolayer. For instance, here we do the scratching. We scratch. We can scratch away the self-assembled monolayer by the mechanical force. We can also remove it by the electrical means. This is called elimination. So we remove self-assembled monolayer from a certain space, certain place. This one is the addition. So we have the self-assembled monolayer transferred from a tape onto the substrate. So this is nothing but deep pen nano-lithography as we have seen today. So the third way is called substitution via in situ addition. In this case, so first you do this method. You do this way. You remove the self-assembled monolayer. So when this part is removed, another type of the monolayer will fill in. It will fill in. This way, this area here, the self-assembled molecule will be different from the molecule here. The last one is also substitution, but this one is substitution via terminus modification. So you scan the tape along the surface through the electrochemical or catalytic interaction. So you can modify the end of this molecule. If you want to learn more about this method, you can go to this very, very long, 52 pages long review paper. But that's good for research, but not no commercial application. This is the millipede. This one is actually a very ambitious idea. This is very, very ambitious idea about 20 years ago, a big project in the European Switzerland. So we know that HTM, scanning tunneling microscope, and AFM, they were both invented by the IBM in Zurich, IBM in Switzerland. So the same people 20 years later, in around year 2000, they proposed this millipede idea. It's for the data storage. On the polymer. So the goal is to replace magnetic recording, to replace the hard drive magnetic recording. Why is it called a millipede? This is the worm of this is the millipede. You have 1,000 legs. Here we have 1,000 of the tips. We have 1,000 of the tips working together. You have higher yield. You get higher yield, higher throughput. Here, each of the tip is controlled individually. This is different from the work by the Northwestern University. In that place, in that work, all the tape they move down or up at the same time. But here, the tape can move up or down individually. We can control them one by one. So now let's look at how to do the data storage. So the data, you can see we have this pit. You store the data. This is like 1, 1 and 0, 1, something like that. For the process, we heat up the tape. We heat up the tape to 400 degrees. Then the hot tip will soften the polymer and sink into it. It will sink into it. This way you have the indentation. This is the writing. Okay, you can see here. You pass the current, heat up the tip, then it will sink into the soften the polymer and sink into it. This is the write process. For the reading is more tricky. In this case, for the reading, the temperature is 300 degrees. You have 300 degrees. You can see here. This is the reading process. So you pass the current to heat up to 300 degrees. But the heat will get lost to the substrate. Then the temperature will be less than 300 degrees. In this case, the tape is on the top of the film. It's far away. The heat loss is not so much. But when the tape goes to the indent, this part is closer to the sample surface, so you have more heat loss to the sample surface. This way, the temperature will be lower. So when we have lower temperature, the resistance will be changed. You can imagine, so the higher the temperature, the higher the resistance. So roughly we have 1 nanometer change of the height. You change 10 to minus 4, the delta R of R, the resistance change. This is how you do the reading process. This is how to do the reading process. So we have 1,000 more than 1,000 tape. This can be used to realize 200 gigabytes per square inch. This is very high 20 years ago. 200 gigabytes per square inch, very high 20 years ago. But for today's hard drive, we have very high. We have 1 terabyte per inch square. So 1 terabyte, this 10 to power 12 is much higher. So now we look at the writing and the reading. But we also need to bend. We also need to approach the sample. So we need to bend the cantilever. So we can exert some forces. Into the polymer. But then you realize that this bending is called actuation. So we need to actuate the cantilever. So this is done by the thermal bimetallic actuation. So we have bimetallic. So that means we have two metal film. But actually here we do not use metal film. So we have one cantilever material here. There is one cantilever material. We have one metal film here. One metal film on the cantilever. But this one is the heating. This is the resistive heater. So you pass the current to heat up this cantilever. When you heat up, the metal here will expand, and the expansion of the metal is more than the expansion of this cantilever. This way, the tape will be bended. The tape will be bent this way. But if you put the metal on the backside, on the backside of the cantilever, then the tape will be bent to the other way. This way, you can control the bending of the tape to have some force onto the polymer. But this is bimetallic activation. So we can look at this is the bimetallic strap. You can see the idea is simple here. You see, this is the without heating. So with heating, this one will be elongated more than the other one. Then it will be bended. So this is also a bimetallic coil. You have two layers of the metals. So when you heat up by this candle, it will expand. So what's the use of this kind of thing? So what's the application for this coil? Because when you heat up, it will expand. So this can be used as the thermometer to measure the temperature. So actually, you can buy the thermometer to measure the temperature of the hot plate. You can buy this like a commercial product used to measure the temperature of the hot plate. It's the same idea. So when you heat up, it will expand. Then you put a kind of needle. So then the needle will rotate to tell you the temperature. So here's the example of the later on they make it even higher. This is 1 terabit. It's 1 terabit per square inch. 1 terabit per square inch. So this corresponds to the casing of the 25 nanometer pitch. So this is the tape, very sharp tape. And this is when the tape when the tape will work. It heated up. But eventually, this one is not very successful. So because, as I said here, there are lots of heat, lots of power, lots of heat needs to be dissipated, and the tape may also get contaminated or get broken or get worn off. This is not very good for the repeated recording and writing and reading. And now we will watch a short video for the millipede. So you pass the current to the writing or to the reading. Now there is a water company. It's called ICHPI. Some of you may know this company. It's called ICHPI. They also use this bimetallic activation for their AFM. They also use bimetallic activation for their AFM instrument. So this company called ICHPI. This is a spin-off company from University of Waterloo, from Professor Rafat Master's group in the Electrical and Computer Engineering department. So actually, there are quite a few nano students who have been the top students, and even for today, a few of the key engineers of this company is the nano student from the from AE program. Here's the idea how this thing works. We have some video here. I will show you some video from this company. Very simple and cheap AFM. So the AFM cost just about a few $1,000s. A single chip AFM. Everything is in this one chip. So you do not need like a lasers for the optical detection, for the normal AFM. So you can see a second video here. So you upload the sample. You got a very easy to operate. Very easy to operate. You do not need to do any alignment. And this is the tape part. So everything is in one cantilever. So everything is in this chip. The reading, writing, activation, detection, everything is in this chip. So this one is actually it's too fast. So this part here, we move the actual for the actual and the y direction, they use the comb drive. You have this kind of thing. So you apply some voltage, it will move in up and in. This is called comb, you know, the comb drive. This is for the XY motion. For the Z, for the bending, for the Z direction motion, they use the bimetallic, as we see here, bimetallic actuation. Yeah. So they use this one, bimetallic actuation for the bending. So as I said, so this idea is not commercially, this is not successful. So the company IBM, they gave up this project maybe year 2005. But some people, you know, they got very well trained, but they know this one does not work. Then the same people, they come out to form another company, which is called Swiss Lithography. They form another company called Swiss Lithography. This company, they sell the AFM lithography equipment. They call it nano freezer lithography. This is the term gets from the Swiss Lithography. This company was later bought by the bigger company. This is the German. This was Switzerland. This is the Germany. Heidelberg Instrument. But they bought this Swiss Lithography. So now they are the same company. But this is the topic of this one called thermal scanning probe lithography. So I got those slides from the Swiss Lithography people because we are in the same WeChat group. If you want to learn more about this process, you can read this review paper, Thermal Scanning Probe Lithography, this review. This one is published 2020. It's published just 1 month or 2 months ago. So for this thermal lithography, we also use the heated tape. But here we have only one tape. We have only one tape. You can have much more control. You can make it, you know, you can do different things with only one tape. But if we have too many several tapes, it's more difficult to control them individually. So first you can use the tape to burn away the polymer. This you can do like a electron lithography. You can burn the polymer. But we can do modern electron lithography. For example, we can do easy grid-scale lithography. So we know that, but we can also do the grid-scale lithography using electron lithography. But this one is not easy to control. But this one we can have nanometer resolution. So that means, for example, if you have the resist. If this is the resist, and this is separate, so you want to burn a hole like this. If this one, see, you want this part to be, say, 20 nanometer. The depth of the hole is 20 nanometer. If you use this method, you can control it to make it 20 nanometer. But if you do electron lithography, you may got 30 nanometer. Because in the lithography, there is no feedback. You do the exposure, then you do the development, then you see how deep is the hole. But when you do the another freezer lithography, there is the feedback. So how to do the feedback? So that when the tape is hot, you burn the hole. But when the tape is cold, the cool down takes a microsecond. When it's cold, you can do the imaging, you can do the inspection, you do the AFM imaging. Then you can check how deep it is. If it is too deep, then you can modify the process to next time you get to the shallower. If it's too shallow, you know, you can modify the process to make it deeper. But because of this feedback by the scanning, cold tape scanning, so you can have very precise control of how deep you get. In markerless overlay alignment, you do not need to put any alignment mark. We know that for the normal optical lithography, we need to put this kind of thing as the alignment mark on the wafer. Then you put, you put the counter pattern, complementary pattern on the wafer, on the photomask. You align the four square with the cross. This is what you do for the optical lithography. But for this process, you do not need to make any alignment mark because you can do the imaging. When you do the imaging, you know where the pattern is. If you know where the pattern is, then you know where to put the pattern. It is non-invasive lithography. We have thermal energy. It only have local heating, thermal energy, no energetic electrons or ions. It can be made tabletop because we do not need a high vacuum or high voltage. We can also do the thermal conversion of the materials. So here we do the removal. We can also do the conversion of the materials. So the heating and the cooling take about microsecond time scale. So here I will show you the video. So I'll show you the video how does this thing work. So now I will show you the video of how this process works. So we want to create this pattern. So we scan from the bottom to the top. So first, on the way from the left to the right, the tip is heated up. The tip is heated. And when the tip is heated, you create the pattern. On the way back, the tip is cold. Here the tip is cold. When the tip is cold, you do the scanning, you get the image. This is the AFM image. That's why you get in situ feedback. That's why it says what you see is what you get. You see the pattern, at the same time. We do not need to separate the metrology or inspection because we can see it already. We do not need to do the imaging afterwards. We can check an online adoption of the patterning every few microseconds. For example, if we see the pattern become too tall or too short, too deep, then we can modify it. When we write the next line, we can modify it so that we know the height, we get the right height. And we can do because we have this feedback. Here again is the process. Hot tip, you do the burning. Cold tip, you do the scanning. You do this cycle. So every few milliseconds, we pattern one line with hot tip. Then we cool down the tip in a few microseconds. Then we do the image. On the way back, we do the image of the written line. Because we have the feedback, we can use the feedback to adapt the patterning, to adjust the writing time or the temperature. Maybe not temperature, at least we can adjust the writing time. Then we can pattern the next line. So here we have seen the material removal. We have seen the removal of the material. So you can see here, so you can do the indentation, you can do the disruption, burn away the material, degradation or disruption of the material. After the material is removed, you can do other pattern transfer. For example, here, this is the thermal resist, AFM resist. You can use this as the mask to do the etching process, or you can use this one as the mold to do the molding electroplating process. Or you can use this one as the template to do the guiding or trapping of the nanoparticles. This is the single resist layer. If we use bilayer, you can transfer the pattern into the substrate layer. Then you can do the deep etching, or you can do the lift off. You can do the metal lift off, or you can modify the process. This is called the selective surface activation. And when you use 3 layers, you have the top resist layer. You have this black color. This is the hard mask layer. They have a thick bottom layer. You can transfer it first etch into the black line hard mask, then you etch to the thick bottom layer. Then you can have very high resolution deep etching. You can also do the lift off. This is the material removal. In addition to the removal, we can also do the conversion. So in the conversion process, we can do the physical conversion. So for example, we can make this part from crystal to the amorphous, or from amorphous to the crystal, or we can also change the magnetic orientation. We can also do the modify the chemical property of the surface. We can also do the addition. We can do like what we do with the dip pen. We put some ink onto the pen. We do the dip pen. We can also do the CVD. So when we have the hot tip, we have the local heating. Then with this local heating and the precursor gas, we can deposit some pattern here. But this one is the resist. The resist material is the PPA material. So this is the PPA. But this one will be decomposed at high temperature. So the tip is 900 degrees. The tip is very hot, 900 degrees. But because the tip is very sharp, like 10 nanometer, we have very sharp tip, only 10 nanometer, but the heat transfer actually not efficient. Even though the tip is 900 degrees, the polymer here, the polymer in contact, the PPA in contact with the tip is only 500 degrees. This 500 degrees, it will decompose this polymer to form something volatile. So this takes about a microsecond. But this decomposition is endothermic. That means the process absorbs the heat rather than release the heat. This way we can prevent the spread of heat. But only this area in contact is heated, area around it not heated. This way we have the localized heating, but no proximity effect. So the resolution will be the same as the tip. If the tape is 10 nanometer radius, you get 10 nanometer resolution. So here are the two examples of what you can do with the this process, nanofreezer process. This is called a faceplate. This is the grayscale lithography. So no other lithography can make grayscale pattern as well as this one. This is the most precise way to do the grayscale lithography. This one is called optical Fourier surfaces. This is also a grayscale lithography. It's very recent work, not published yet. So we can also do the alignment. We can also do the alignment for the 1D and 2D materials. For example, this is 1D nanowire. This is nanowire. So you want to put a side gate. You put a side gate on the left side and on the right side. You make the transistor. You have the source, drain, and the gate. So how to do this? So first, you have this nanowire. So you coat the PPA layer. You coat this PPA, this polymer, onto the nanowire. Then you do the imaging process. You do the imaging. So you see something like this. And from this image, you can say that this is the edge of the nanowire. Then you can design the cat pattern. Then you do the nanofreezer patterning. You burn away the pattern. So after you burn away this pattern here, you can do the metal lift-off or the reactive ion etching to do the further process. In this case, you do the lift-off to pattern the gate onto the side of this nanowire. So the main limit for this one is really good for research. But some people may think this is too slow. For example, when we use one tape, single tape, it writes about 1 millimeter per second. This is for the line writing. When you do the area writing, you write about 1,000 micrometer square per minute. But this number is not very low, but you can see it's only 50 nanometer pixel spacing. This is not very good resolution. If we have 10 nanometer pixel spacing or 20 nanometer pixel spacing, I think it will be a smaller area. But even though this area, 1,000 micro square meter per minute, is still too slow. So the natural solution is to do the multi-tape extension. You have this way. We have many tapes. You can have higher throughput. So the last topic is the scanner near field optical microscope. It's called SNOME. Here's the idea of this. Here's the idea of the SNOME. So this is also called scanner near field optical microscope. It's called ENSOM or SNOME. The first is called near field scanning optical microscope, or this is scanner near field optical microscope. So they are the same thing. So we know that when we do the optical microscope, optical imaging, the resolution is limited by the diffraction of the light. The resolution will be close to the wave loss because of the diffraction. But when we have this kind of setup, so we have this optical fiber, the central one is the central part is hollow. We have this hollow fiber, so the light will be guided through this hollow fiber. But when they are very far away, you have the less diffraction. This is the far field, so you have this diffraction. But when the tape is very close to the surface, then there will be no diffraction. So broadly speaking, if the aperture specimen separation is less than half of the diameter of the aperture, then the resolution will be limited by the diameter of the aperture rather than by the wave loss, because there is no diffraction. For example, if the diameter here is 50 nanometer diameter, the gap here may be 25 nanometer, then the resolution will be about 50 nanometer. Then you can scan this fiber along the surface. Then you get the 2D image. This is why it's called scanning. You do the scanning, you get the 2D image, as you can see here. So here you have the optical fiber, hollow optical fiber, so the light is guided through the fiber, through the aperture, and comes to the sample. This is called a near field illumination far field detection. So when the light comes to the other side, you have this PMT, photo multiplication tube to detect the optical signal. You scan along the surface, then you can have the 2D imaging. You need PMT rather than like a CCD camera, because the signal, very small aperture. This is very small aperture. The signal is very weak. Very little light can come through. We have very weak signal. You need this photo multiplication tube for the detection of the photons. Now here the resolution, this is DNA. So the resolution here is about 30 nanometer. We know that DNA is only like 2 or 3 nanometer, but here it looks like 30 nanometer because the aperture size is 30 nanometer. Okay, this is the enzyme as known. So how to make the fibers? How to make the hollow fibers? So we have this is the hollow fiber. We have this a single mode optical fiber with the core material already removed. Then you heat up, you burn it, you heat up to melt it. This is glass. You use the fire. You use the fire to melt the glass. Then you draw it, you pour it. But when you pour it, it will be broken. When it is broken, will be very sharp. Then while it is heated, you can bend it. Then you can mount it to the holder. So you have this snub tip by this company, Nanonix company. And the second question is how to approach the surface. We know that for the case of normal AFM, so we have the tip. And we shine the laser beam. Then we go to the detector. This is the normal AFM. This is how you control the cantilever approaching to the surface. But in this case, it's very sharp. You cannot do the same measurement. You cannot do the same optical on the cantilever. Then people use the tuning fork, because this is a tuning fork. So you mount the fiber onto this tuning fork. Then you have this excitation. We have the excitation of the tuning fork. You excite it, then there will be vibration. So when the tape is very close to the sample surface, you have the damped. So the vibration will be damped. You can see farther away, large vibration. Very close to the sample, small vibration, because the vibration is damped by the sample surface. This way, by maintain the oscillation amplitude, to the middle point. This is the working point. To maintain this oscillation amplitude, you can maintain the distance from the tape to the sample. This is how you keep a track of how to approach the tape to the sample surface. So what we can do with the lithography? So the simple idea, we can do the direct serial writing. So we have the tape here. If this you put the photoresist, this is the photoresist. So you can write across the photoresist. In this case, we use 1805 photoresist, give you 500 nanometer thick of the photoresist. You do the exposure like this. You move around, you get the pattern as you want. Here the resolution, they do the development, you get the resolution. It's not very good. It's about 200 or maybe 300 nanometer, but it is still better than the normal optical lithography. Thank you.